Swayam Prabha. Digital India. Educated India.
Okay, welcome everyone. So, now we completed our study of the steepest descent method or more generally line search methods in the previous lecture. So, what we will now analyze is the basic issue of how fast these methods can be. Okay. So, for we will now discuss what the rates of convergence or the speed of convergence of algorithms. Okay. So, in order to do that, we need to first have a notion or a definition of what we would call the rate of convergence, right. So, let me define that for you to begin with. So, the rate of convergence. So, let R k be any sequence of numbers that converge to R, say, or R star, say. Okay. So, we say that the order of convergence, the of convergence, the order of convergence of R k to R star is the largest value of beta greater than equal to 0, such that this quantity, this limit which is greater than equal to 0, this limit as k tends to infinity is finite. Okay. So, what does this mean? It basically tells you what is what's the largest value. So, if this quantity is finite, if this limit is finite, it effectively tells you that for large enough k, R k plus 1 minus R star, the absolute difference between these two, is roughly equal to some constant times R k minus R star raised to the largest such value of beta, right. So, for if you are if you are that's effectively what this particular thing is telling you. So, if you are going, so for large enough k, your iterates behave in this kind of way, right. So, if beta is and to be precise here, I should be taking the lim sup. Okay. So, if beta is taken, it turns out to be 1, we say it's we say it's linear convergence, which means that the distance between R k and R star, which so which means the updated distance between where you want to be and where you currently are is roughly equal to a constant times your earlier distance R k minus R star. Of course, this because this is convergence, eventually the R k minus R star will decrease to 0, as will R k plus 1 minus R star. But what we are asking is how much progress are we making relative to where we were at, how much progress have we made in the new iteration relative to where we were in the previous iteration. right, and that is what's captured being captured by the rate of convergence. Now, if beta equals 2, we say it's quadratic convergence, and this is usually very good, because if you can get, if your iterates can converge quadratically, that means you are making the progress you are making is much more than what you, at each iteration you're progressing much more than you had in the previous iteration, right. And uh, if uh, uh, if it turns out that beta is equal to 0, sorry, if it turns out that beta is greater than, sorry, not 0, not equal to 0, if it turns out that this is if it's greater than 0, greater than 1, and if it turns out that beta is greater than 1 and this constant here and this constant is actually equal to 0. Okay. In that the constant here, sorry, the constant here is equal to 0, then we say it's super linear convergence. Okay. So, now to let us what we will do is uh, we look at the rates of, by looking to study the rates of the of convergence, we will look at first the simplest form of a descent method, which is the steepest descent method, and that too we will study it only on first on quadratic functions, because once you it turns out that a lot of what we want to say can what we want to learn about the rates of convergence can be learned from just this. Okay, so let us look at this function f, which is half x transpose q x minus b transpose x, and I am going to take q to be is symmetric and positive definite. Okay. The gradient of f you can evaluate is equal to q x minus b, and x star is then the unique, let x star be the unique solution, x star, which is the minimizer of f, is the unique solution, I mean the minimizer x star is the unique solution of q x equals b. Alright, now the good thing about quadratics is that you can calculate a lot of these you can calculate a lot of these things in closed form. So, in fact, when we are doing this, since we are doing now if you are doing steepest descent with line search, the actual step that minimizes the function along along a certain search direction. So, the search direction for us is pk, as which is equal to minus gradient of x k. So, we can actually calculate f of x k minus alpha grad f of x k. So, this is equal to, say, remember, f of x k plus alpha p k. So, we can actually calculate this in closed form. Closed form, we can minimize, find the alpha that minimizes this. It turns out alpha, so find alpha, it turns, and set that as alpha k. So, it turns out alpha k is equal to gradient of f at x k transpose gradient of f at x k divided by okay, transpose q times the same gradient of f at xk. Okay. So, the iteration then becomes xk plus 1 equals xk minus this term, gradient of f at xk transpose gradient of f at xk divided by gradient of f at xk transpose q times gradient of f at xk, the whole thing times gradient of f at xk. So, this actually gives us, you can now substitute this in all of these expressions in in terms of this formula, this expression q that where the gradient is equal to qx minus b, and you can actually get you can actually get this in a much more explicit form, where xk plus 1 can be written in terms of xk. Now, it turns out that you can also, therefore, using this, then we can also calculate compute from here how the distance between xk plus 1 and x star, and the distance between or the distance between f of x minus f of x star. Let us write this as so first let us define the following. Let us define norm q norm of x as x transpose q x. Okay, so, this is effectively a kind of a skewed or a tilted norm with where I am taking the weighting matrix as q. And now we can, it is very easy to show that from here that x minus x star squared q, sorry, this squared, this is the squared q norm. This squared is actually nothing but f of x minus f of x star. All right. And now, using this we can derive the following theorem. The theorem says the following. Now, with when the steepest descent method is applied to the function f with exact line search. What do I mean by exact line search? By exact line search, I mean that is where we are finding alpha in closed form, right. So, this is, let me write this here, this is what is called exact line search. What we did in the previous lecture, where we were looking for alphas that satisfied the Wolf condition, those are what are called inexact line search, because we are not actually finding the exact minimum there. We are just putting conditions that are terminating alpha must be satisfied. Okay, yeah. So with exact line search, then we, what do we get? Then we find that xk plus 1 minus x star squared in q, the q norm, is less than equal to lambda n minus lambda 1 divided by lambda n plus lambda 1, the whole squared, times xk minus x star q norm, where what are these lambdas? These lambdas, this is lambda greater than 0, greater than or dot dot greater than lambda n, are the eigenvalues of q. So, these lambda 1 to lambda n, they are the eigenvalues of q. Now, where lambda 1 is the smallest eigenvalue, lambda n is the largest eigenvalue. And so, now what is this relation saying? This relation, this q norm squared, is nothing but the difference between the function value and the optimal value of the function, right. So, this q naught, so the difference between, so if effectively this here, this term here or this term here essentially is capturing something like an error, the error that you have or the departure that you have from your optimal solution. So, the error, it says, is less than at iteration k plus 1 is less than equal to this constant times the error that you had at iteration k. And you can see what is this constant. Well, this constant is so this constant is something that depends on the eigenvalues of q. So, usually what happens when you run this sort of steepest descent algorithm on a quadratic function like this. So, remember this was a convex quadratic function, because I assumed that my q is symmetric and positive semi-definite. So, if I look at the contours of q, so let me draw this thing here for you. So, sorry, contours of f. So, this would be, let us say, is my outermost contour. This is another contour inside. This is another contour inside. This is another contour, etc. Right. So, if you do this, here is what we get. So, you start from here, go here, okay, and then you do this, and then one goes, say, maybe I will draw one more contour in somewhere here, in some intermediate contour. That takes us here, and then another one takes us here, another one takes us here, another one takes us here, etc. So, you can see what the way I have, from what I have drawn, these are the iterates that your algorithm has produced. It is starting from this particular contour. This is your this is the point x 0. From here, it goes in the direction of it goes in what is the steepest direction of steepest descent. It keeps going till it can minimize the function along that direction. That minimum gets attained here at the second point here. So, this is point x 0, this is point x 1. Then it moves, then it again goes in the direction where this is minimized, where it goes in the direction of the negative gradient, minimizes the function along that particular direction, reaches point x 2, then again goes in the direction where along the gradient, now negative gradient at x 2, etc., etc. Right. So, this is what happens when you apply steepest descent to this sort of quadratic problem. Now, here this was a very simple problem, because we actually knew where the solution was, and you could have found the solution by simply inverting the matrix Q. But you could but we are trying to see how the behavior of steepest descent method actually works. Now, what you can observe here is the main thing you can observe here is that the steepest descent method tends to do this kind of zigzag. It keeps going zigzagging this way all the way towards the solution, and the reason for that is this kind of zigzag is because of the skew that is introduced by the matrix by your Hessian matrix Q. If the extent of zigzagging really depends on how much you need to keep changing your directions of descent, and that itself depends on how your eigenvalues are, how different your eigenvalues are. So, if in the simplest case, if all the in the simplest case, what does this say? Well, in the simplest case, if all the eigenvalues are equal, what would happen? If all the eigenvalues are equal, where in that case it would be Q would be all would essentially be an identity matrix, say all the eigenvalues are equal to 1. In that case, what would happen then lambda n would be equal to sorry, I should have put a weak inequality here, my mistake. In that case, lambda n would be equal to lambda 1, and then this term would be 0. The term in this inequality would be 0, and xk plus 1 would be exactly equal to x star. So, in the case when the eigenvalues are all equal, the first step itself would not point in this sort of direction, but rather point straight towards the minimum, the actual global minimum of the function. It would point you to this direction directly. But because there is a skew in the function, the shape of the function takes you in this sort of path. First you go in this direction, then you go in this direction, then you go in this direction, then this way, then this way, then this way, etc. Okay, and the extent to which you will end up zigzagging really depends on the condition number, or the ratio of the largest to the smallest eigenvalue, right. So, as the condition number grows larger, the contours of the quadratic become more elongated. They tend to sort of get more stretched out. The contours become stretched or elongated, and more zigzagging occurs. Nonetheless, one thing that this result actually tells us directly is that the steepest descent method converges linearly in general, right. So, the convergence of the steepest method is linear. So, this sort of there is all this zigzagging, but it does converge, but it converges only linearly. If your condition number is mild, means close to 1, then the contours themselves would look more circular, and the first try itself will get you close to the solution. Okay. So, that the actual number of iterations would be the actual number of iterations then would probably be a little lesser. Okay. So, but so here is the main thing then, that the rate of convergence depends on the extent of curvature, or how different the eigenvalues of the lowest and the largest eigenvalues are, right. Okay. All right. So, this is what we find. So, let me make a note here. So, the steepest descent converges linearly on this sort of quadratic problem. Now, it turns out that for problems that are more non-linear, where not necessarily quadratic, some pretty much similar sort of result holds. So, I will just state again the theorem for you. Suppose f from Rn to R is twice continuously differentiable, and that iterates generated by the steepest descent method converge to X star with exact, okay, let us say with exact line search. Line search converge to X star at where the, if I look at the Hessian of f at X star, this Hessian is positive definite. Now, let R be any scalar that satisfies this. Lambda n is a scalar that lies in this interval, lambda n minus lambda 1 divided by lambda n plus lambda 1 to 1, where lambda n greater than equal to dot 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 lambda 1 greater than 0 are the eigenvalues of the Hessian at X star. Then for k large, we have f of x k plus 1 minus f of x star is less than equal to 0, less than equal to r square times f of x k minus f of x star. Now, you can see how this, why this is the case. The f of x k minus f of x star is essentially the same as this error term, and this is what appeared here. So, what is happening here is that as you if you are considering a twice differentiable function, and you can look at the iterates that come from the steepest descent method with exact line search, and suppose they converge to an X star where the Hessian is positive definite, then the function value or the error term is going down to 0 linearly is showing linear convergence. This you can see, and the rate the constant outside again depends on the condition number of the Hessian. Okay, the condition number of the Hessian at the point where the function converges. So, what is the lesson here? The lesson here is, one, of course, that the rate of convergence of steepest descent method is linear in the best case, and second is that the quadratics, the study of the steepest descent method on a quadratic function gives you a good sense of what would be happening for a more general nonlinear function. And the reason for that is basically the rate of convergence at the end of the day depends essentially on how the function, how the iterates behave close to the solution, because it is eventually a limiting quantity. And since the rate of convergence depends on and when you are close to the solution, a quadratic approximation of the function is a fair approximation. So, quadratics tend to give you how the performance of an algorithm on a quadratic tends to give you also how the algorithm would perform on more nonlinear type of functions, right.